Good morning, everyone. I'm David Robel, Dean of the College of Arts and Sciences and Professor of History, and I am thrilled to welcome you all to Stony Brook's Quantum Frontiers, a fantastic opportunity to highlight the many ways in which our university sits at the leading edge of today's vital developments in quantum science and technology. Today's celebration also showcases the partnership between the College of Arts and Sciences and the College of Engineering and Applied Sciences. And I'm pleased to acknowledge my friend and colleague, Andrew Singer, Dean of the College of Engineering and Applied Sciences, for his collaboration in making this event possible. Together, we're bringing you exceptional faculty from each of our colleges who will discuss their particular areas of quantum expertise. Andy, thanks for being such a great partner. I'd like to also thank Rachel Rodriguez, Director of Communications for Arts and Sciences, and Deborah Scala-Jokas, Director of Communications for CEAS, and their teams, and to the Order Center for Communicating Science for their expertise and guidance, the Wong Center team, and so many others working behind the scenes for all of the effort that went into making this celebration possible. Thank you. Now, as a historian, I'd love to reflect on how we might look back at the past, a generation or a half century from now, and I firmly believe that when we do that, we'll remember this week, and we'll remember Stony Brook University as the epicenter and the wellspring of a new set of quantum frontiers that will change the world for the better. So, without further ado, I am honored to present President Andrea Goldsmith, the 7th president of Stony Brook University, the State University of New York research flagship, and as we love to say, and we can say together if you like, the #1 public university in the state of New York. Prior to her appointment in August of last year, President Goldsmith served as Dean of Engineering and Applied Science at Princeton for 5 years and spent 21 years on Stanford's engineering faculty. A champion of access, opportunity, and upward mobility, President Goldsmith credits her entire public school journey from grade school and community college through earning her bachelor's, master's, and doctoral degrees at UC Berkeley as the foundation for her success. Her pioneering research in wireless communications that we heard about just prior to this morning's session has sparked innovative technologies, and she's lent her expertise as a board member of several companies, including Intel, Medtronic, and Crown Castle, Inc. With more than 3 decades of experience in university leadership, teaching, and research, President Goldsmith is focused on achieving Stony Brook's bold aspirations and meeting the needs of the communities it serves by accelerating its excellence across all dimensions of education, clinical care, research, and innovation. Thank you, President Goldsmith, and congratulations on your inauguration.
Thank you, David, for that wonderful introduction, and good morning and welcome. I'm really thrilled that you've joined us today for a panel where experts across the evolving and dynamic field of quantum science and technology will discuss their research and this revolutionary potential. I want to personally welcome SUNY Trustee Stoller, whose vision, wisdom, support, and friendship has been invaluable to SUNY, to Stony Brook, and to me throughout my time as president. Thank you. This is a pivotal moment for the State University of New York at Stony Brook as we secure our spot as the leader in the country and the world in quantum technologies. The faculty members that you will hear from shortly, along with their brilliant students and researchers that they are training as the next generation of leaders in the field, are at the forefront of driving forward this transformative technology that will fundamentally change communication, computing, sensing, and so much more. And here at Stony Brook, we are setting a bold vision to be the leader in accelerating discovery, not just in quantum technologies, but across the spectrum of technology and science and social science and the humanities to solve humanity's greatest challenges. That's what I'm so proud of in leading this university as a public flagship to make the world a better place for its people. And this mission includes building on our leadership and our excellence in our impactful research across complex areas, including quantum communication. Today's presentations and panel will provide insights into the various frontiers in science and innovation in the quantum realm. Everything from material science to computing to educating the next generation of quantum scientists and engineers, and to networking, quantum networking, which is truly magical. And you will hear about the future of quantum in each of these areas. We are so proud that the thought leaders that you're going to hear from here at Stony Brook are leading the conversations spanning quantum science and technology in its future. Now, in my wireless communication lecture this morning, I discussed briefly how we're at the dawn of the quantum information age. And that's similar to where wireless communication was when I started my wireless research career in the late 1980s. We certainly had no idea at that time what wireless communication would become. And we're at that same point in quantum. In fact, if you reflect back to the 1980s, phones had to connect into a socket. I don't think young people today, our students, would have any idea what that meant. And computers also had to connect into the wall. Today, we take completely for granted the fact that we can send a video or a text from anywhere in the world on these small, inexpensive phones in our pockets. But at the dawn of the cellular technology age back in the 1980s, when I started doing research in this area, that notion seemed magical. But if you can envision a future, you can go build it. And today, sending quantum information anywhere in the world also seems magical. And we have created that magic right here at Stony Brook by building the largest quantum network in the country. Stony Brook, in partnership with Brookhaven National Lab, has established a secure quantum network which is currently running under your feet across Long Island and into New York City. And this network, which will eventually extend across the great state of New York and then throughout the nation, will not only enable secure quantum communication for financial transactions, for health data, for everything that needs to be completely secure, unbreakable by the codes that can break current encryption. So we're not only enabling secure quantum communication, but our network will also support the quantum Internet of Things by connecting distributed quantum computers, sensors, and any other quantum device anywhere in the world will connect into the quantum network that will be built starting right here at Stony Brook and on Long Island. We are committed as a public flagship, as the #1 public university in New York. Yay! We're committed to enabling New York's national leadership in the groundbreaking area of quantum research. And we're incredibly grateful to partner with our great state for their support, including the $300 million investment that Governor Kathy Hochul announced here on our campus in my 6th week of my presidency, investing unprecedented amount of money to establish a quantum research and innovation hub here at Stony Brook. And this investment will secure Stony Brook's national leadership in quantum research and impact long into the future. As we expand our footprint at Stony Brook across Long Island into New York and across the country, it was recently announced that Stony Brook would be launching the Stony Brook Quantum Institute with Eden Figueroa, our amazingly brilliant quantum scientist, at the helm of this important initiative and institute. The institute is about both education and research. The education will span students from high school to grad school and will also educate postdoctoral scholars and visiting faculty. And the research in that institute will support collaborations across the different areas of science and engineering and technology needed to drive forward quantum networking, computing, sensing, and simulation. Across SUNY and here at Stony Brook, we're working to accelerate quantum research by providing opportunities and spaces for researchers, students, our amazing industry partners, and experts from around the country and around the world to collaborate together to drive forward this field at this very exciting moment. I'm proud to introduce two of our remarkable students, Jamie Grant and Angelina Lavigny, who will be introducing our presenters and panelists this morning. Come on in. Jamie Grant is a sophomore physics and maths double major with a minor in philosophy. She is a Simon STEM scholar and a member of the National Society of Black Physicists chapter at Stony Brook. Jamie is also Black and Latino Initiatives Council peer mentor and serves on the Cass Dean Student Leadership and Advisory Council. Let's give her a round of applause. And Angelina Lavigny is a senior journalism major with a minor in applied mathematics and statistics. She served as editor-in-chief of The Statesman, and that's our local newspaper that I get very exciting and interesting questions from on a regular basis. And she's also the founder of the podcast SB to MD, bringing her talent, skills, and passion for science writing to her work every time she interviews a professor or a student. Let's give her a round of applause also. I'm so inspired by students like Jamie and Angelina. They are diverse, they are talented, they are passionate, they are brilliant, and they are the future leaders in these complex fields. And it's not just these two amazing students. What struck me as Stony Brook president every day of the last 8 months is how incredible our students are. They're passionate, they're talented, they're grateful for the excellent, affordable, and accessible education at Stony Brook that unlocks their full potential and brings bold, innovative ideas to their studies and research. Here, our students have the opportunity to bring the ideas that they have out of their labs and to make an impact on our research community. And we are so proud and pleased to be able to educate students like them and to call them our alumni when they leave this place and brag about the incredible things that they're going to do. Let's give them again another round of applause. So let me close by saying I'm so incredibly excited for the conversation and insights we're about to hear today that will uncover the possibilities of quantum to revolutionize communication in ways we have not yet even envisioned. Our strides and impact in quantum technology will continue to grow and propel New York to be a leader in this pivotal field and in technology overall. I invite all of you in the audience to enjoy these amazing presentations and connect with one another, because you never know where great ideas will come from. Challenge yourselves throughout these talks to envision what a quantum future will be. And then we hope you will join us on this journey to lead this next era of quantum technology right here at Stony Brook. Thank you so much.
Thank you, President Goldsmith, for that wonderful introduction. For our first speaker, we are very pleased to welcome Scott Carney. Scott joined the Department of Mechanical Engineering as chair and professor in the fall of 2025. His work focuses on the interaction of light and matter at the atomic scale, and how those fundamental discoveries can be translated into real-world technologies. Today, he'll explore a critical question: how do we move quantum breakthroughs from the lab into technologies that we actually build and use? Please join me in welcoming Scott Carney.
Thank you, Angelina. Thank you all for being here to celebrate the inauguration of President Goldsmith. As you've heard, President Goldsmith is an expert in information and how we communicate it. Quantum information, science, and technology is about to change everything, making her a leader for our time. What do you want to see in the second quantum revolution? Do you want quantum-enabled gravity sensors to listen to the songs of the Earth? Do you want quantum magnetometers to read your mind? Do you want quantum computers to simulate and discover new drugs and new cures? Or do you want a perfectly secure network for privacy and transactions? Well, all of these technologies are here. They're ready for us. But they won't be a revolution, they won't be your revolution, until we can manufacture them. And that's what we're working on. So to understand the arc of technological revolutions, come with me to the first quantum revolution. It's 1925. And physicists are confounded. There are befuddling results, like why is the spectrum from the sun in discrete lines? Why are there isolated colors? Why does the hydrogen atom have a negatively charged electron that orbits a positively charged proton and yet doesn't just spiral into the nucleus? Why are there not enormous amounts of energy coming out at extremely high frequencies from every hot body, the so-called ultraviolet catastrophe? Why? Physicists have no real unified answer. What they have is a patchwork of results and theories and little fixes. What they are forced to conclude is that what they need is not a new theory, but an entirely new framework for understanding what the world is. The world of Newton and Galileo is a world of things you could hold that had positions and momenta, and events took place at times certain. But the world of quantum mechanics is a world described by a quantum state. It doesn't live in a three-dimensional or four-dimensional space-time. It lives in a high-dimensional Hilbert space. You don't ask questions like, what happens if someone throws a tomato from the third row? Well, let's not run that experiment today, okay? No tomatoes from the third row. But we ask questions like, what's the probability of finding the tomato at some place in the room at some time? And it's worse than that, because not only are positions a thing of Newton and Galileo, but things themselves are ideas of the past. What if that tomato becomes an apple and a potato on the way up? It's entirely possible. Well, maybe not entirely possible, but it's among the probabilities you have to calculate. And so this is a really strange world. It's a world of debates about the health of cats and the gambling habits of God. It is a world that we just weren't prepared for, but it's also a world that reveals remarkable results. It explains things like semiconductors. And in 1947, scientists and engineers at Bell Labs build the world's first trans-resistance, three-terminal semiconducting device. The transistor is born. Now, who's heard of a transistor? Okay, what do you think the revolutionary impact of the transistor was? Almost nothing. Almost nothing. For 10 years, the transistor replaces vacuum tubes. It brings us transistor radios and better hearing aids. But in 1958, a photographer and physicist named Jack Kilby figures out how to use the methods of photography to project the structure of a circuit into a semiconductor. He builds the world's first integrated circuit. The integrated circuit he builds is on germanium, and at the same time, Robert Noyce goes out and figures out that if instead we build things on silicon, we could really manufacture at scale. So by the mid-1970s, we've got pieces of semiconductor, pieces of silicon, with thousands of transistors on them. Thousands, I tell you. Today, of course, it's tens of billions. And we manufacture those chips in the millions. And that's the quantum revolution. The first quantum revolution is here today, and it's manufacturing. Your life changed not because we figured out why spectral lines are discrete. Your life changed because we figured out how to make chips at scale. Manufacturing is the revolution. All right, so what do you want out of the second quantum revolution? Well, today, you're going to hear about how we're training the next generation of quantum innovators and the weird world of programming quantum computers. And you're going to hear about a network being built in the tri-state area led by Stony Brook University. You're going to hear about exquisitely sensitive quantum sensors, graviometers and magnetometers. And you're going to hear about two-dimensional materials, flatland for electrons. Will two-dimensional materials be the key that unlocks robust and manufacturable quantum devices? I don't know, but stay tuned and find out. Thank you.
Thank you, Dr. Carney, for your very insightful presentation. I'd now like to introduce Jennifer Cano. Dr. Cano is an associate professor in the College of Arts and Sciences Department of Physics and Astronomy, who is presenting Frontiers of Quantum Materials. Dr. Cano received her PhD from the University of California, Santa Barbara. She is a theoretical physicist whose research focuses on the emergent properties of quantum materials and specifically topological phases of matter. Professor Cano developed the theory of topological quantum chemistry, which combines group theory, topology, and chemistry to predict new topological materials. Please join me in giving a very warm welcome to Dr. Cano.
Probably most of you have one of these in your pocket. But have you ever thought about how much energy it consumes? In fact, phones, networks, and the computers and networks that power them make up 10% of global energy consumption. That's a lot. It's on par with the airline industry. So where is all of that energy going? Well, one place where it's going is dissipation. So when electrons travel through wires, they bump up against each other. They bump up against the sides of the wire. And all of those collisions create heat, which is wasted energy. So what we need is something more efficient than that. What we have right now is something that you can think of like traveling on the 495. You can think when you're sitting in heavy traffic, everyone wants to go in the same direction, but yet there's collisions. And those collisions waste time and energy. What we need is something more like the Japanese bullet train for electrons. On a train like this, all of the cars move together. They move in phase with each other. They move efficiently, and there's no collisions. Quantum mechanically, we call this phase quantum coherence. In a quantum coherent state, every electron knows where every other electron is. Therefore, they can move efficiently around each other, efficiently and without any collisions. Macroscopically, we call this phenomenon superconductivity. So where can we find materials that exhibit superconductivity? Well, the place where we're going to look is in two-dimensional materials. So behind me is a picture of the structure of graphene. Graphene is the first discovered two-dimensional material. Each one of those balls is a carbon atom, and you can see that this entire material is just one atom thick. So graphene has fantastic properties, and in fact, its discovery was the subject of the Nobel Prize in 2010. But why are we interested in graphene? For a couple of reasons. So because it is so thin, it forces electrons to spend more time near each other, and that helps them to get into that quantum coherent state. But second, because it's so thin, you can stack layers of graphene on top of each other, and you can arrange them in different ways, and that gives us the ability to create designer materials with tunable properties. And at the very frontier of this field of two-dimensional materials is what we call twistronics. So imagine that you have two sheets of graphene and you stack them on top of each other with a small twist angle. What you can see is that as you change the angle between these two layers, they form this large-scale interference pattern. And as the angle changes, the size of that pattern changes. And that change that you can see with your eyes, well, electrons also see that, and it dramatically changes their properties. And in fact, in graphene, as you change that twist angle from just 0 degrees to 1 degree, that structure changes from being a metal to an insulator to a superconductor. Does this solve all of our problems? Well, not quite yet, because this superconductor can only operate at very cold temperatures. And so this prompts us to ask the question, are there other materials, other two-dimensional materials where we can look that will exhibit this property? In fact, there are many, 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 many other two-dimensional materials. A recent database actually predicts 10,000 of these. And each one of these two-dimensional materials can be stacked and twisted on top of each other. So now we have a bigger problem, which is in this vast phase space, where should we look? And so that's the problem that my group is taking on. So in the past year, we developed an efficient algorithm to search through this phase space. So we start with that database of 10,000 materials. And we filter those for the ones whose properties might be suitable for realizing these twisted bilayers. And that actually brought our list of 10,000 materials down to a smaller list of only 100. And now we want to study the properties of those bilayers. And so this is actually a very computationally hard problem. Even with all the computing power that we have here, we still can't do it exactly. But we have a cool approximation to make, which is that instead of looking at the entire bilayer by itself, we can zoom in on small regions. And when you zoom in on those small regions, it doesn't look like it's twisted anymore. And so thereby, that's actually a problem that we can study efficiently. And so what we do is we stitch together the properties of electrons in all those small regions, and that tells us how the electrons behave in the bilayer. Finally, then, we have the properties that we need, and we can try to identify which of these materials is going to be suitable for creating the next superconductor or some other entangled quantum state. So last year, we actually carried out this algorithm. And so that gives us the table that I'm showing here. What this table is showing is the properties of electrons in each of those bilayers and the range of twist angles over which we think our results will be accurate. And so what we want to do next is to hand over our predictions to our experimental colleagues who can test and validate them. And what they will find is the next Japanese bullet train for electrons. And that material will be the backbone of the next generation of energy-efficient electronics.
Next, we're excited to welcome Hanya Chuk Choi. Gupta is next? I'm so sorry, I had it out of order. Next, we're pleased to welcome Himanshu Gupta. Professor Gupta is a faculty member in the Department of Computer Science, where his research focuses on quantum networking and computing. Gupta got his PhD in computer science from Stanford University and B.Tech from IIT Bombay. In this talk, he will demystify the magic behind quantum technologies, breaking down concepts like entanglement and superposition to show how they actually work. Please join me in welcoming Himanshu Gupta.
Hello. Good morning, everyone. So, the purpose of this talk, called Promise of Quantum Computing, is to convince you all in the promise of quantum computing. So I want to first tell you the basic element of what makes quantum computing so magical. So one of the things that it gives us is it can potentially give us speed beyond imagination. And the fundamentals behind that, in short, is as follows. In the classical world, an element of computer is essentially a bit, which is 0 or 1 at any point of time. In quantum, the basic element is a qubit, which essentially is actually 0 and 1 at the same time. Think of it as a coin. In the classical world, we have coins that are either at heads or tail. In the quantum world, a qubit is essentially a spinning coin, which, when measured, boils down to either head or tail. What does that give us? So if we have a system of these 100 qubits, of 100 spinning coins, we can actually manipulate 2 raised to 100 possibilities in parallel, because these qubits can essentially be in 2 raised to 100 states at the same time. That's actually huge. That can, in the computing world, can dwindle millions of years of computing time into seconds. But there's a catch. The catch is that even though you can explore 2 raised to 100 possibilities at the same time, when you actually want to read it out, you only get one of those outputs at random. So what that means is that we need some creative algorithms to actually leverage this parallelism. So what I presented in the last slide was kind of some theory, some potential, but there is actually a proof of this promise. That is Peter Shor's algorithm. So consider this problem that you have a large number, think a few hundred digits, and you want to factorize it. That is, you want to find a number that essentially is a factor of this large number. In the classical world today, we don't know how to solve this problem in less than millions of years. Or if we were to do what we know, it'll take us millions of years. And that actually is the basis of our current encryption systems. But if we had a quantum computer, we can actually solve this problem in mere seconds. And that is due to the very creative quantum algorithm that was designed by Professor Peter Shor, who's at MIT now, in 1994. This algorithm essentially has changed the world of quantum computing. It has given us the foundation of this promise that if this is possible, then maybe lots of other things are possible. So this essentially gives us the promise that quantum computing that we hold with. Beyond speed, quantum can also make impossible things possible. In particular, in the classical world, we know that it is impossible, technically impossible, to do communication from one point to another, which is fully secured. But in the quantum world, it is indeed possible to have a fully secured communication from point A to point B. And the fundamental reason why it is possible is that it is due to this no cloning theorem, which essentially says that it is impossible to make a copy of a quantum element, that is a qubit. Now I want to discuss what I consider the only magic in science, which also plays a big role in what quantum can provide, which is called quantum entanglement. I want to just briefly describe what it is. Consider you have two qubits, and locally you do something to it. Think of it as making them twins of each other or correlating them. We call that quantum entanglement. Now let's say we separate them by a large distance. Think Earth and Mars. Now, if we read one of these qubits, if you think of them as spinning coins, if we actually measure one of the coins, that is, we basically make it either head or tails by slapping it down on the table, then what happens is instantly the other coin, which is millions of miles away, also collapses to a state, the same state as the state that we collapsed here. This suggests they are possibly connected by an invisible wire, but we don't know why that happens. And this is what Einstein himself, 100 years ago, found it very shocking, and he actually termed it as spooky action at a distance. Now, this entanglement is actually essential for many applications of quantum, in particular in building a robust quantum network that you will hear about soon. So finally, I want to say that fundamentally the promise of quantum computing is in huge speed that it can potentially offer to solve some of the problems. And the second is to give us fully secured communication. And the biggest of challenges, or main challenges, are that we actually need to build a robust quantum computer, and we need creative quantum algorithms. Thank you.
Thank you, Dr. Gupta. I am now incredibly pleased to introduce Angela Kelly. She is a professor in the College of Arts and Sciences Department of Physics and Astronomy who is presenting Breakthroughs in K-12 Quantum Education. Professor Kelly teaches and advises students in the PhD program in STEM education at Stony Brook University. She directs the Masters of Teaching Physics program and teaches undergraduate physics. Her research interests include pre-college and university quantum, physical science, and engineering education, reformed STEM teaching practices, and science teacher recruitment and retention. Please join me in welcoming Dr. Kelly.
Thank you, Jamie, for the wonderful welcome. It's a pleasure to be here with such a distinguished panel. And as Dr. Goldsmith alluded to earlier, in order to facilitate the promise of quantum technologies, we need to educate the workforce of the future. And that begins at the pre-college level when students really become inspired to pursue various careers. So in our project, we are looking at ways in which we can make quantum education accessible for pre-college students. And this is through several NSF-funded initiatives that I have been involved with my distinguished colleagues Tzu-Chie Wei and Dominic Schnabel in the Department of Physics. And our approach to quantum education is very much multidisciplinary. It is a multidisciplinary domain involving aspects of physics, chemistry, mathematics, etc. And the way to communicate that to a younger audience is to embed multiple ways of representing these basic phenomena of quantum physics. So I'm going to talk about several aspects of these initiatives today. First, this diagram may look confusing, but this is our conceptual continuum for introducing these ideas to both pre-college students and their teachers. And we start with classical ideas of wave behavior, including diffraction and polarization. And this leads to some quantum ideas, typically taught by Dominic, and bringing in thought experiments such as Wigner's friend and Schrodinger's experiment. Then that's followed by an introduction to quantum computing, where students use IBM Composer to construct basic quantum circuits and learn about ideas such as entanglement and quantum key distribution. A unique aspect of our program is the emphasis on quantum career preparation, educating students on the quantum-adjacent coursework that's best going to prepare them to pursue quantum study at the post-secondary level and beyond. Now I'll talk about the 3 different initiatives that we have put together. First are our outreach programs for middle and high school students. To date, we have reached over 800 middle and high school students through summer camps here at Stony Brook University and at the New York Hall of Science in Queens, and one-day quantum teaching labs where students come in classes here to the university to see our labs and do experiments. Our data have shown that these initiatives have improved student knowledge in all of these domains: classical physics, quantum computing, and we were very pleased to see that students increased their quantum career aspirations as a result of participating in our program. The second set of initiatives, it was for the International Year of Quantum last year. So our team secured additional funding from the National Science Foundation to host 2 very exciting conferences here at the university. The first was for school district leaders. Long Island has 125 school districts. We had 150 superintendents, assistant superintendents, science directors come to Stony Brook to hear talks from policymakers in New York State, to hear talks from our researchers here at the university, and hear from teachers and students who are involved in quantum learning in formal schooling. These representatives of school districts represent collectively 200,000 students in the region. So our program has had tremendous reach and impact. Building upon this conference, we had a second conference a few months later for over 80 teachers. They started right here in this room, heard some similar talks, and then went outside to the atrium to do hands-on experiments in classical physics, and quantum computing. Again, it generated excitement and a grassroots effort to bring quantum ideas into pre-college settings. Finally, our last set of initiatives centered on working with middle and high school teachers to empower them to create curricula, to teach quantum ideas in their existing classes, and to design new coursework for their schools. This is quite a challenge for these teachers, but we've worked to date with over 200 teachers, and each of them teaching approximately 100 students. You can see that the reach has been enormous. So we're looking to have them embed quantum principles in their existing courses and create new ones. So where are we going from here? What are the next breakthroughs that we want to experience in quantum education and workforce development? Well, we would like to bridge opportunities for pre-college students to enter Stony Brook University and engage in the world-class education that we offer to prepare the next generation of quantum workers. We also want to involve students from two-year colleges to bridge their opportunity to come to Stony Brook and continue their education. And lastly, we would like to facilitate pathways for our undergraduate students and graduate students into the quantum workforce. We feel that these breakthroughs have been significant. We can certainly build upon them. And we believe that Stony Brook University is positioned to be an international leader in quantum education and workforce development at all points in the academic continuum. Thank you very much.
Now we are very excited to welcome Hanya Chuck Choi. Chuck is an assistant professor in the Department of Electrical and Computer Engineering, where his research focuses on quantum sensing, networking, computing, and photonics. His work explores how tiny artificial atoms inside diamonds can be used to build quantum technologies. Today, he'll show what this could mean for the future of quantum computing. Please join me in welcoming Chuck Choi.
Hello, everyone, and thanks for the nice introduction. Today, I'm going to talk about integrated quantum technology happening here at Stony Brook. Why are we so excited about the quantum technology? That is because it's a transformative technology that changes our life. Here is a good example. Here is a Google's quantum computer that has a 50 qubit. For the small computational task, it's going to take 2 weeks of time for the largest supercomputer in the world, which quantum computer could do it within 200 seconds. However, this is not the end of the story. For the large computational task, like the drug discovery, it's going to take 10,000 years in largest supercomputer in the world, while quantum computer, again, could do it within 200 seconds. So again, it's not the marginal speed up. It's not like iPhone 15 to iPhone 16. It's a transformative technology that makes the impossible to be possible, as Gupta also mentioned. So 50 qubit is awesome, but we want to make it larger. We want to have millions of them or billions of them on a tiny scale so that we can use it every day. And we want to borrow classical wisdom. Here is a classical computer, the first generation of a computer called ENIAC. It was made out of 18,000 vacuum tubes, operated by people plugging one and the other. Nowadays, we are having this tiny microelectronic chip that has 20 billions of transistors on the size of a fingernail. If you're closing up this microelectronic chip, there are billions of wires hanging around, transferring the information from one device to the other. This is why our IT revolution was possible. So here in Stony Brook, we are working on integrating quantum devices in large scale so that we can do a large-scale quantum information processing. The first effort is integrating these quantum devices with a photonic circuit so that we can route the light coming out of qubit to the direction we want. The second effort that I'm going to talk about is integrating with microelectronics. In this platform, we are integrating microelectronics with the quantum devices so that we can control a large number of devices all individually through the existing mature technology. How can we make the quantum devices? That's the starting point, right? I mean, I'm using diamond. Who doesn't like the diamond, right? It's beautiful. It's great. It's made out of the carbon atoms. It's making the crystal lattice of a diamond. But then we have so many nitrogen in the air. Somehow this diamond is catching the atoms in the air in their diamond. What he found is that this is an artificial atom or qubit that we can control and use it as a qubit system. Diamond is expensive, right? So I'm using actually lab-grown chemical diamond that looks like a tiny plate. We are making large number of quantum devices on this diamond with a qubit in diamond. The size of these devices are a fraction of a human hair thickness. So you can imagine that we can make a large number of qubits in this tiny chip. We have a quantum chip, now we need a microelectronics. We are designing and making this microelectronic chip from the semiconductor company that makes the chip in your iPhone, right? We are exactly using the same process to make a large number of transistors and bringing these two chips, quantum chip and the microelectronic chip, we press them hard, twist it so that the quantum devices are sitting on the microelectronic devices. So finally, this is the device that we made. And I actually brought it here, right? So if you cannot see it well, sorry, but that's intended, right? This is the tiny chip, tiny quantum computer on my hand or in my pocket, right? We have these thousands quantum devices on this chip with 4,000 qubits that are individually controllable by this microelectronics. So now we have everything. What is the problem? My students doesn't want to characterize 4,000 qubits one by one all day, all night, right? So we actually made a quantum robot microscope. This quantum robot microscope has a camera. This camera is scanning the sample with a QR code. So if you're seeing here in the middle, I brought some movie clip. This quantum robot microscope scanning the sample, registered the devices, location of the qubits, property of them, so that you're putting the sample in the night, coming back to the lab in the day after. With the coffee, you can see the statistics of these quantum devices and choose the best one for your own purpose. We are also scanning the laser frequency so that we see how these qubits are interacting with the lasers. Finally, we are generating the qubit map down there, qubit graph down there, so that we can create the quantum algorithm on our quantum machine. Before wrapping up, I want to cite the father of a semiconductor technology, Gordon Moore. He says the value of a technology grows as it scales. And in Stony Brook, we scale the quantum technology. Thanks.
Thank you, Dr. Chuck Choi. Last but not least, I'm very excited to introduce Eden Figueroa, a Presidential Innovation Endowed Professor in the College of Arts and Sciences Department of Physics and Astronomy. His presentation is titled Building the Quantum Internet. Professor Figueroa is the inaugural director of the Quantum Institute at Stony Brook University and leads the university's Quantum Information Technology Group, where he has developed scalable room temperature quantum memories and entanglement sources, aiming to construct the first working prototype of a quantum repeater network. He holds a joint appointment at Brookhaven National Laboratories. Without further ado, please join me in giving a warm welcome to Dr. Eden Figueroa.
Hey, good morning, everybody. How's everybody doing? I hope you're doing amazing, and I hope you really enjoy these wonderful talks by these brilliant people. It's always great to be last because then the work is easier, as many things have already been said. So let's just start by talking about this building the quantum internet. So this morning, we heard from Andrea, actually a great talk, where she discussed a little bit of how the internet came to be about, right? So we're going to review a little bit of the recent past. What does it mean? What is the quantum internet? So as it was discussed in today's talk, we saw, right, that the internet and the information transferring that it requires have been built with the purpose of reaching out as many people as you can, right? And then, of course, in doing that, we perhaps didn't take much care of security, right? So now, one of the greatest opportunities in further developing the internet is to look into ways that we can make the information transfer more secure, right? And this is where quantum enters the fray. The fundamental problem, perhaps, in the design of the internet is that information needs to be amplified, every 50 miles or so, there is amplification systems, either for wireless or for optical, that then allow you then to amplify the information. The problem there is that once you amplify, you actually lose the knowledge as to whether the losses in your system are due to just the physical effect of transporting the information, or is you actually have an eavesdropper that is looking at your information. And this is why then your information then goes into some server like TMC, and you really don't know until you actually see it published on the internet, right? And then so here is where quantum enters the story, right? And then so what we want to do now is we want to build a new layer of the internet in which the information, it's no longer encoded in millions and millions of photons that are transmitted on the internet, but rather we're going to go into the lowest level of energy available, basically going to the single particle of light. These particles are called photons, and then you're going to use the properties of these photons to then encode the information into it. As Himanshu was already telling us, there is two keys that are important here. If you use these single photons, right, then you can build these Schrodinger cats in the form of photons that will allow you then to create superpositions of information, right? So then you enhance the space where the information is transmitted. The second thing that he also mentioned, right, is the creation of entanglement, pairs of qubits that now share these invisible correlations, and then if you send them into two different places across several hundreds of kilometers, if you poke one, the other one also transforms. And from these fundamental tools, this is when then the quantum internet can be built. Here are some internet properties, right? If you transmit qubits and then you verify whether or not eavesdropper touch upon those qubits, and then by measuring you transform them, then you ended up with quantum cryptography, originally proposed in 1984 by Bennett and Brassard. If you use entanglement in combination with those qubits, you can do Star Trek-like experiments with photons in which you then quantum teleport the information from one place to the other one. Very importantly, the information does not go in the communication channel anymore. Entanglement does, and therefore is as secure as the physics laws actually allow you to do it, right? We also heard you can also use this quantum internet now with all these properties to start connecting the qubits that Chuck was mentioning, and then try to entangle those qubits in different quantum computers via these entangled photons. All right? So now let's look at the present and what we're doing right now here in Stony Brook. I actually want to use this opportunity to celebrate my team and all the persons that work with me, certainly the most wonderful persons I've ever met in my life. And here, this slide actually shows you a celebration, right? In the last 5 years, right, starting in 2021, we started building what is now the longest quantum network in the United States, certainly in North America. And what I do, right, every time we install a new device in one of these nodes, right, across Long Island, I take a picture so you actually see what we're doing. You actually see my students there going to different places. We drive all this quantum equipment that some of our colleagues mentioned, and then we go into data centers across Long Island, and then we install it there, right? So for example, Jen mentions about superconducting systems. Here is a picture of one of my students, Anthony, setting up a superconducting nanowire detector that allows them to measure these photons. Here's another picture of my student, Jackie, installing a quantum entanglement source in one data center over there in Westbury. So then my invitation is that next time you go to a strip mall here on Long Island, please look around. And if you see a geeky looking character with long hair, he's probably installing quantum equipment somewhere around there. Pictures prove this, all right? So what I'm gonna show you now next, right, is for us I was thinking about this. Imagine when Thomas Edison first lit the streets of New York City just with light, right? That was basically a little bit more than a few hundred years ago. So in May of last year, I'm going to show you that in my next slide, right? This was our we're lighting the world kind of moment. This is the first time that these networks come to life, right? And then we actually lit Long Island with quantum entanglement, right? So you actually see here the signals. This is really the first time that everything arrived. The signals that you see here are actually showing that those photons are arriving in pairs across 140 kilometers, right? And then what we do is we actually do these spooky interactions at a distance experiments that then show that the particles remain entangled after propagating in commercial fiber, each of these pairs across 140 kilometers, right? So now this works. This is truthfully the longest entanglement distribution network right now in the world as we know it. So this is actually very nice, and it's very proud that we made it with Stony Brook talent. So thank you for that. Now let's look at the future. The future is so bright, and you heard it from my colleagues. I mean, there is so much talent here. So now let me just briefly discuss what we're going to be doing soon, like in the next few years, right? The first thing, let me introduce you to our quantum robot strategy. Here comes a quantum robot. I hope you can see the robot. My students work very hard to try to see the robot. So we heard from President Goldsmith, right, that we have some fundamental investment here from the state of New York, right? So then the head of the robot is this Quantum Research and Innovation Hub that we are building, right? The heart of this is going to be the new building that is going to be created on campus, that is going to be our quantum beacon of hope of everything that will be happening, where we will bring quantum computers. Chuck is going to build all these computers so then we can have them there. And then we're going to have our quantum network control center that will control all quantum network operations across Long Island, right? Very importantly, the arms of that robot are going to be, you heard it before, our newly funded Stony Brook Quantum Institute that is going to put together physics, computer science, and electrical engineering, so then we can make Stony Brook the first quantum-connected campus in the United States. On the right-hand side, you see the other arm, which is going to be our innovation arm, where we're already working with some of the best startups, quantum technology development companies, to start creating what is going to be the quantum corridor of New York, developing technologies and setting up startups, right? And then finally, as you already saw here, the skeleton, the legs of all the operation are going to be our network that we are now constructing and building upon, that I will show you in our next slide. This will be my last slide. This is now New York Quantum Internet, right? The New York Quantum Internet is going to be the extension of all the things that we're doing on Long Island, and you already see here. This is now, as is being published, you can actually see this document. The SUNY Quantum Stride document tells us about the strategy that we're going to follow in the next 10 years to really build that quantum Internet of Things. Very importantly, right now we're setting up some massive collaborations with Cisco. You know Cisco, the largest networking company, certainly in the world, and NicerNet, which is the largest research network here in the state of New York. So we can actually build this network. You already see here the different stages that we're planning it, right? Basically, Long Island and Albany at the beginning, later Syracuse, Binghamton connections, eventually Buffalo, literally repeating the same technology that we already established in our Long Island network here. So anyways, with this, I finish this small talk. All I want to say to you is please be sure that the quantum future of Stony Brook is extremely bright, as bright as this slide that I'm seeing here. So here is for several more decades of quantum research in Stony Brook. Thank you so much for everything.
Something remarkable just happened, I think. We had a dean, a president, 2 students, and 6 faculty members present, and we're on time. I want to welcome our speakers. Welcoming everybody back to the stage. We're going to have a brief panel. Dean Singer and I will ask a few questions, and then we will see if we've got a few minutes to turn it over to all of you for some of your questions. All right. Scott, I'm going to begin with you. Let's talk about quantum teleportation. Could it ever have potential for transfer beyond information?
It's a great question. So first of all, teleportation is always a bit tricky to talk with a a lay audience about because Star Trek has set the bar pretty high. So there are lessons to be learned, though, from classical information theory on this point, which the number one thing I'd like to emphasize is that information and energy at some level are equivalent. You cannot convey information without transmitting energy. This is sort of the heart of the resolution of the spooky action at a distance paradox, that at the end of the day, you have to move something, real mass or energy, which themselves are equivalent. So could we move, could we teleport something more than information? That almost just misses the point that stuff and information in the quantum world are sort of all the same thing, in the same way that this idea that the Newtonian world has passed us by and there are no definite things with definite positions anymore, information, energy, and mass are all interchangeable.
All right. Andy, thank you.
So Angela, this one's for you, and for all the parents that are in the audience that want to have a less than spooky conversation with their children about the promise of the quantum future. So what are the fundamentals that we need to know to make it accessible for, let's say, a K through 12 audience?
Well, I think we heard from several of my colleagues today, Himanshu, Aiden, Jen, Chuck, really all of them, on the basic fundamental concepts that underpin quantum technologies. What we have found with middle and high school students is they're tremendously interested in potential use cases. So what problems in the world today can be solved by quantum science and quantum computing? So they're very interested in knowing about sensing, and that seems to be the most immediate way in which we can implement these technologies. They're fascinated with what Aiden does with the quantum network. The network is right here in their backyard. They are also very interested in the potential of pharmaceutical discovery facilitated by quantum science and quantum computing, and how that can improve health and solve problems and cure diseases. So that's from a cognitive standpoint. I'd say from an attitudinal standpoint, also as parents, it's important for us to communicate to our students that quantum careers are not just for those with innate brilliance. So we need to diminish that notion among students that there are multiple entryways into these careers from the technician to the graduate level. And we need to communicate to our children a growth mindset. And that is a belief that anyone who develops an interest in this field can pursue this field in the future.
Wonderful, thank you.
Right. Chuck, this one's for you. So you showed us that image of the first classical computer, this massive room-sized object, and then you pulled this tiny object from your pocket. I'm wondering how long before quantum computers become ubiquitous in the way that cell phones and laptops have?
I think it's a very good question, and I think we are better than the older generations. So we could do that quicker, I think. And might be like slightly different form. It might not be like, everyone putting quantum computer on the phone, or maybe it's in that phone, right? Nobody knows, but like everybody is using the ChatGPT every day. We don't have a server in our phone, right? Like still, we can access those like through a cloud. I imagine that we could have a quantum data center that everybody could just use it on the background of your phone. Or even like quantum sensors. Angelina talked about that really in a nice format. But for example, I'm making centimeter scale quantum devices. Centimeter scale quantum sensors. I don't see there is no reason for having these things on the phone, for example, within say next 5 years. So I think some matter of time probably we could talk about whether it's say 5 years or 10 years or 20 years. But I think it's coming. I'm sure, in 20 years, we're going to have everything everywhere. Yeah.
Amazing.
This one's for you, Jen. Andrea spoke earlier today about sensors that we might like to embed into bridges that would last for 10 years or more. And those of us who have to plug in our cell phones or multiple devices every single night want to know, where can quantum materials get us really in terms of energy reduction and dissipation? Are we ever going to get to a point where we're not plugging everything in every single night and wondering whether or not it charged? And are there other places where we'll see a noticeable difference in energy use due to quantum devices and materials?
Great, thanks. So I first want to emphasize that the technology that we're thinking about is still at the very fundamental level. So we're trying to get the operating temperature from temperatures that are only in the lab to, say, room temperature or some other reasonable operating temperature. But once we get to that point, I think the biggest impact, although I motivated it with our personal devices, I think that the biggest impact is probably in the large data centers, like which was just mentioned. For example, data centers that are storing the stuff that you have in the cloud or that's powering AI. I think that's the place where probably there's the biggest possible gain from this kind of technology. And then we'll see how much gain there is in our personal devices.
Okay, thanks. Himanshu, this question is for you. Though, Eden, you touched on this in your presentation. So we hear a lot about quantum computers enhancing cyber security through entanglement. And I'm just wondering if the benefits of quantum encryption outweigh the potential dangers of quantum decryption. Is there a world in which quantum decryption can overtake quantum encryption?
Yes, so thank you. That's actually a very insightful question. So as you saw in my talk, I presented two sides of the coin. One was that if we were to have a quantum computer, then it'll actually break the encryption that we rely on today. On the other hand, it also gives us, so that's the negative, it'll break what we have now. And the positive is that it promises fully secured communications. So which one offsets the other? So the reality is, if we be honest with ourselves, if quantum computers never come into being, then what we have is largely sufficient, assuming that nobody comes up with a classical algorithm to factor a large number, which we don't believe is possible. And if quantum computers were to come into being, then yes, we need more newer encryption methods, and that is a whole area of post-quantum cryptography, which is essentially working on exactly that problem, and things are happening in that field. And over the long term, if quantum computers do come into being, then we do believe that we will have more positive, more solid, more foolproof communication, secure communication. Thank you.
So then, Andrea showed us images of the early ARPANET that became the internet, that became the World Wide Web. But it was decades before we went from an interconnection of supercomputers at laboratories and universities in the United States to every one of us having connectivity in our pocket, where we just sort of wake up and expect to be able to use the internet. So when will the quantum internet really be built out? Not just in a lab, not just an experiment for people with long hair and PhDs in fancy trucks on Long Island, but when is every kid going to wake up and jump right on to the quantum internet?
All right, that's a complicated question. Let's say, what I'm going to say is we just had a town hall in New York City in which I think it was 33 or 34 different states came to see what we're doing here. So I think really from the time that people think, let's build regional networks, to the time when you have a national network, there are several decades that need to pass. So then the infrastructure is built that can connect the small regional efforts. So say right now we are at that point where every single state in the next 5 years is going to start building a small regional network. So that by the time we go into like a national network that is based on entanglement, there are several technology frontiers that still need to be crossed, and there has to be a very large investment from the federal government to start uniting them. So I would say to see a US quantum internet that is entanglement-based with repeaters, it's probably 2 or 3 decades before we can see that as a backbone, which probably means perhaps 4 decades before people can actually have their optimum Wi-Fi with entanglement. Yes. Mm-hmm.
Okay, so I'm just counting decades and wondering how many I'm going to be able to see. But going to see whether or not I can hang on that long, What are the ways that we're going to use the quantum internet first? Is it going to be security? Is it going to be computing or something else?
So I think there's two applications that I think are now coming online. I think the first very interesting application is this construction of hybrid quantum classical networks, in which, let's say, 70% of the network still uses high-speed traffic, as we normally do, and then you embed quantum characteristics into this, for example, by having quantum cryptography protecting the classical data, or by having quantum teleportation services that do the most critical data in the network, but not all of it, right? I think companies certainly like Cisco and Siena and financial companies like JP Morgan Chase and so forth, they are really interested in doing this. I think in the horizon of 5 years, we will see regional networks that do this, right? At the scientific level, quantum sensor networks, right, that already connect some form of sensors like the one Chuck was showing us today, in which by connecting several sensors, you use the long baseline of all these nodes that are separated by entanglement. There are several applications like quantum astrometry and global positioning and things that we believe that can be enhanced by having these sensors entangled in these long networks. I think now as these sensors have been developed and the networks are developed as well, regional quantum sensing networks are probably in the horizon of another 5 or 10 years. Those will be the two examples that you will see coming soon. Right.
Wonderful.
Right. Andy, we'll close out with a question from me to you. Earlier this week, we had a wonderful SUNY AI symposium here at Stony Brook. Can you say a little about AI and quantum, how they can help each other, and maybe tell us a little bit about the Genesis mission and how federal investment may help us build those connections?
Sure. Well, that's one of the big questions and one of the reasons that the Genesis mission was kicked off. It was great to be in D.C. a couple of weeks ago and watch Andrea up on stage telling the world how Stony Brook is front and center in everything related to AI and quantum and semiconductors and this massive investment from the federal government in using AI to advance science. That's really what the Genesis mission is about. And thinking about how quantum and AI work together, on the one hand, if we have quantum computing and networks that can communicate quantum information, then our ability to train massive, unimaginably powerful AI systems can be unlocked. You heard earlier that we can solve problems that could take 10,000 years, or training of the next generation algorithm that might take 10,000 years, we could do in 200 seconds. So that's one way in which they're entangled. The other is in the development of quantum systems. We need to be able to simulate complex chemical, physical properties and devices. And we can't quite do that, as Andrea said earlier, if we don't have the precise mathematical models for them, or if we have computational limits. But we can use AI to accelerate and to enable computations in ways that are otherwise more difficult to do. So these two are part of a spinning coin of science, I think, and engineering, that really will enhance one another. And that's where the Genesis mission really is important. And it's phenomenal that we've got all pieces of this happening right here at Stony Brook.
Thank you. I'm going to turn it over to all of you for any questions you might have for any of our panelists up here on the stage. So time for a couple of questions. I see a question right in the middle. There we go. Fantastic.
Good morning. As a literary scholar, I must say that I came into this not quite knowing if I would understand anything. I'd like to thank all of the panelists for making it very user-friendly. So my question is, probably for Eden primarily, are you saying that you are the first to develop this prototype with the quantum repeater network? Are other nations engaged in similar endeavors, and are you working or considering working internationally or globally to help to develop this kind of technology?
Absolutely. In the last few months, I engaged into some international trip to find out what is the status quo of different networks across different places. I can tell you that Europe is building right now the largest quantum cryptography network in the world that will connect all the European countries using quantum cryptography. And what they're doing right now is they're setting up committees in every country that then will guarantee that the networks that are built in Poland are compatible with the networks that are going to be in France and so forth. So that is happening in Europe. That doesn't use entanglement, and this is what they are developing now. Our network is entanglement, so it's slightly different. The countries that are developing networks like ours that use entanglement and quantum memories and repeaters, the most advanced one right now, it's the German quantum repeater program, which they are building now networks using the Deutsche Telekom network to then connect Berlin, Munich, Frankfurt, and Stuttgart using entanglement, just like we're doing here on Long Island. Actually, we had some great conversations with them to see if we can collaborate in some ways. And of course, the one that everybody heard about is these developments that they're doing in China to develop their entanglement distribution networks. They went into a different way. We are using fibers because, of course, Long Island is like the nation capital of fiber infrastructure in the United States. But in China, they're doing it with satellites, right? They're actually putting quantum technology in the satellites, launching the satellites, and then having these entangled photons coming down. So different technologies, different approaches, but certainly the world is going quantum internet these days, yes?
All right. Maybe we've got about 3 minutes left. Just one or two more questions? We're pointing in different directions.
There's a hand high in the air over there.
I think she was the first to have her hands up.
Please.
Thank you so much for seeing me. So I have two questions, but they kind of interlap. So this is primarily for Drs. Cano and Figuera, but anyone who can answer. The first, so you mentioned how quantum coherence can't work at room temperature. So this has been bugging me for months, but I read a paper like in January about how photosynthesis uses quantum coherence, and that happens at room temperature or hotter. So like, how does that work, or how can we build off of that? And my second question is, I attended the Turning Tides event on Monday, which was about climate action for President Goldsmith's inauguration. And one of the things that came up is, well, in the last 30 seconds, was data centers and how they're terrible for the climate and all that. So how can we make sure that when we're building these quantum infrastructures that they don't end up causing the exact same problems?
Right. So I answer the physics question, and then I let somebody else answer the other question. So this is a great, insightful point that you bring. Normally and traditionally, we always talk about quantum that needs really coiled environments. Original experiments, for example, for quantum computers were done in Josephson junctions that are literally at 30 millikelvin, as cold as you could possibly get. And the original experiments with atoms were done with Bose-Einstein condensates that need to be going all the way down to the hundreds of millikelvins via laser cooling. I keep here doing a different approach that uses literally room temperature systems, as in like 30 degrees Celsius in the laboratory. And in order to do this, you just have to do, let's say, a clever way in selecting the atoms that despite being in motion, they still maintain the coherence, and then play a few tricks. I'm actually very happy to tell you that we actually have the only patents in the US for quantum memory operation at room temperature. And this is really the key gizmo that then will allow the construction of these quantum repeaters in these internet networks. Yeah, so that was...
Okay, maybe I can say something about the first part of your question, which is actually also a really insightful question, which is if we're trying to solve a problem of energy efficiency, are we actually using more energy to solve that problem than we are actually helping? And I definitely don't have the answer to that question, but I guess what I would hope is that whatever solution we come up with would have such a long-term effect that the intermediate period of 10 years or 20 years, whatever it takes to come to the solution that we need, hopefully would be worth the energy investment for that very long-term gain.
I saw a question from the Dean of the Stony Brook Libraries, Dean Karim Bougida.
Yeah, thank you. I have a maybe hard geopolitical question. So, China government is spending more than 17 billion, and we're not spending that much. If we all corporate, private, and everything, it's close to 12 billion. In terms of prediction, is your prediction based on this funding model? Like, what if the federal government will spend more? And you said it, you prefer that the federal government will invest more. So what's the new prediction? And also, how can you handle global governance with this, with different political models?
Wow. So what if the federal government were to invest on a much, much higher scale? Can we cut that time? Can we reduce it significantly, the time for the core discoveries? And thinking in terms of quantum in a global context and the political complications that surround it. So thanks for a very easy question for everybody to grapple. All right, I think so. Himanshu.
Okay, so research is complicated. I mean, we can, the best way I can answer this question is take an extreme case, right? If the funding were to go to zero, of course, it'll prolong the time. If the funding were to go from 20 billion to 200 billion, I'm very, very sure that it'll reduce the time to discoveries. How much is complicated? So that's the extreme case scenario. That kind of answers the question that yes, it will have an impact. How much increase in the money will have an impact on how much decrease in the time of discovery? That's too complicated. I can't answer that. But I would say, yes, it can. And I personally also can see the funding that I've received has had a huge impact on whatever I've been able to achieve. So I think it will. How much is complicated to answer? That's my answer.
Chuck?
The new National Quantum Initiative that's currently under consideration in Congress is trying to shift the emphasis from basic science to commercialization. So by the federal investment coming in to support the basic science, which is so critical, they're hoping that the commercialization side will attract more venture capital, which will thus increase the amount of investment. But it's critical to have the federal support both in terms of basic science and in educating the workforce. So we're really hoping that this bill is passed very soon.
I could also comment on it. I think, yeah, like definitely more money helps, but also how it's spent matters probably more. Like, for example, education, we really need a large number of workforce development there. We just like purely like don't have enough like people who could work on it. There was an exploration phase before where we are exploring what technology could be how applied. Nowadays, like, it's moving more for the, like the startup or like, the small business, even like, building the components of like this large scale system or ecosystem, right? So I think, yeah, like definitely as Himanshu said, like how much is the problem? Like how much money and how much like we could shorten it matters, but also how could we spend those money might matter, like in a good direction. And I see everything positive, so yeah, stay is good.
Yes, question right here, row 1, 2, 3, 4, row 4, in the middle-ish, over to one side. Yes, it was you all along.
If you had a magic wand and you could direct venture capital funding in 1 or 2 specific areas that would help push the field forward, where would you want it to be invested?
I'm going to turn this over to any of the other 7 people on the stage.
Quantum sensing.
I think there's a couple of problems that I think will massively accelerate this. I think there needs to be a lot of investment in figuring out how do you go from 100 qubits in a quantum computer into the 100,000s that will make the difference so then you can run quantum algorithms. Of course, lots of companies are working on this, but this is a not solved problem. So if venture capital will invest in that will be massive. The other one is this story of the quantum repeater that then allows entanglement to travel over longer distances so then we can get to the internet network of the United States. Those are 2 of the problems that still don't have a full technical solution. So then a lot of investment in that from the private sector will do wonders so then we can achieve larger quantum systems in a shorter time span.
I would just add that one of the areas, it hasn't really been talked about much in the panel today, but the potential for quantum technologies to improve medical imaging, to provide sort of crispness of imaging that's hundreds, thousands of times better for us in terms of our healthcare providers viewing images of what needs to be diagnosed, how severe a condition is, I think there's tremendous potential for quantum science to improve human health.
So yes, I wanted to say that what Eden said, those two problems are kind of related in some sense. So fundamentally, yes, we need very robust quantum computers, which can have a large number of qubits. And if we are able to build a network, we can actually connect smaller computers to essentially take the role of a big computer. So in some sense, building a quantum network is related to the ability to build large computers. And that is, in my opinion, the fundamental problem that we need to solve. Thank you.
Okay, thank you. We have one last question. I think row 4, right there, yeah? Yeah, it was you. Yep.
All right, this is a question for Angela, Jennifer, and Eden. Is the evidence of quantum entanglement, does it underscore that the classic understanding of the fabric of space-time, that it's fundamentally flawed or incomplete?
All right, you talk about insightful questions. That is really insightful. So I'll discuss this from a point of view of theory, right? I think normally there's this connection, and I think that happened from the theoretical level, where people talk about entanglement, right? What does it mean? I think we have taken a very practical approach of, we don't really know why it happens, but we're using it. And then there is a point of view of dynamics and non-relativity and so forth, right? That really discusses how space and continuum works. Now they're actually coming together, right? Into something that is called EP means EPR, right? So Einstein-Rosen bridges is a concept of wormholes, right? And the same guys, Einstein, Rosen, and Podolsky, also developed the concept of entanglement, right? So they already kind of knew that was going on, and then so now we're going back into this. So then the current hypothesis, and I really say this hypothesis because we cannot demonstrate it yet, is that when you build these particles, when you make them in these machines that we show in our slides, they actually open a wormhole, like a tiny little wormhole that then allows these variables, right, to then be exchanged across a different space-time that is not the one that we're using to transfer the communication. So then physics is good, and we don't violate causality, but you gotta expand, right, and then not think about this as separate things, but actually one and the same, in which entanglement modifies space and time. And this is what then allows, now it's not gonna be spooky, but just a simple interaction at a distance. Right? That's all my 2 cents on this, all at the theoretical level, I must say that. Anybody else wants to pitch in on this? Very interesting question.
I'm going to stay in my lane right here.
All right. I think what I'm going to do is Andy, Scott, Jen, Chuck, Himanshu, Angela, Ed, big hand for our presenters. And our wonderful student panelists as well. If you could stand so we can recognize Jamie. Thank you. And thanks everybody for being here, for your attention. We've got another Presidential Inauguration Week event just about to begin in a few minutes. Thanks for being with us.